In this video, we're going to see carrier distributions in BJT. To be specific, it's minority carrier distributions in BJT under active region of operation. So let me take the BJT structure here. I'm taking this to be x-axis, and this is emitter, this is base region, this is collector region. And as usual, as we have considered PNP transistor, here also we are taking PNP transistor, P plus, and base is N and collector is P. Now the doping concentrations on emitter is Ne, on base Nb, and on collector Nc. And as we are discussing about the active region of operation, when BJT is in active, the emitter junction is forward biased and collector junction is reverse biased. Hence, I've shown here that the depletion widths here are smaller at emitter junction and larger at collector junction. Now, coming to the doping concentrations here, we know that Ne is far greater than Nb and Nb is greater than Nc. Now the minority carrier concentrations in the emitter, which is let's say called under equilibrium Ne naught, which is given by Ni square over the doping concentration in the emitter. And minority carrier concentration, which is hole concentration in the base, which is Pn naught, is given by Ni square over Nb. And electron concentration in the collector under equilibrium is Ni square over Nc. Now, having known the doping concentration in emitter, base, and collector, we can say that Ne naught would be smaller than Pn naught, and Pn naught would be smaller than Nc naught. Let me show the equilibrium minority carrier concentrations in this figure, somewhat like this, where this is Nc naught, this is Pn naught. Now, on the x-axis, let me take this to be the origin reference, and this is W, the base width here, which is effective base width. And this point is xc. Now as the emitter junction is forward biased, that's why we have shown the depletion width is smaller. Now electrons from the base side would get injected into the emitter side, and as they diffuse through the emitter, the carrier concentration would decrease. And assuming the length of the emitter here is greater than the diffusion length of electrons in emitter, the carrier concentration would change like this. Now coming to the holes injected from emitter side to the base side, obviously would be very high because it's highly doped emitter. Hence the carrier concentration on the base side would be higher in concentration. But if you observe this width W, always we tend to have it very small compared to the diffusion length of holes inside the base, in which case W by Lp is very less than 1. And as the depletion region here is higher, and as the collector junction is reverse biased here, there is high electric field here, which is directed from N side to P side. The holes that are coming here would get swept as soon as they reach this W, which means the carrier concentration should become 0 when it comes to x equal to W, because there is electric field which would take away any holes that are present here and send it to the collector side. Hence, the carrier concentration should become 0 at x equal to W. At x equal to 0, the carrier concentration would be high. As W is very small compared to Lp, we'll take this a linear profile. When we come to collector junction, which is reverse biased, the current that would be flowing is because of the minority carriers. Of course, here the minority carriers in the base now are holes which are accounted as part of the current flow already, which is ICP. Now the current that we have to see is because of the electron concentration in the collector region. Electron concentration should be 0 here, and it would change like this. Here we have shown all the minority carrier distribution in emitter, base, and collector. Now if we remember, the currents that we had was emitter current, which was given by IEN plus IEP, and the collector currents we have discussed were ICP plus ICN. Now, of course, IB was given by IE minus IC. Now, we need to find all these components depending on the carrier distributions we have here. So, the current, we can say IEM, the current flowing because of the electrons which are ejected from base to emitter, that is at this point, is QAD, the diffusion coefficient of the electrons in emitter. So, I put DE times del N over del X at X is equal to minus XN. So this equation IEN can be shown as QADE and E naught over LE, that is the diffusion length of electrons in emitter, times e power VEB over VT minus 1. This is one equation. Now coming to IEP is given by minus QA, the diffusion coefficient of holes in the base, which is n-type, that is dP del P over del X at X is equal to 0. So that's the carriers flowing per unit time at this point at X equal to 0. We need to find what is P of X. Looking at this carrier concentration distribution, we can say that Pn of X is equal to Pn of 0. Let's say we know the carrier concentration at X equal to 0 at this point, times 1 minus X over W. So if you look at this, at X equal to 0, we have Pn of 0. And at X equal to W, it becomes 0. So it's a linear distribution we are taking here. And of course, we have Pn naught, which is equal to Pn naught times e power VEB over VT. Now, IEP can be written as QADP Pn naught over W times e power VEB over VT. This is another important equation. Now we know the terms IEN and IEP, which means we know IE. Now let's find what is IC here. So let's find what is ICP first, which is minus Q A dP del P of X over del X. Of course, at this point, it is at X equal to W. If you see here, the amount of carriers flowing per unit time at this point would be the amount of carriers crossing this depletion region. So that's what we want to find, which is the ICP, the current because of the holes flowing through the junction from base to collector. So as we know what is P of X here, so ICP is equal to, it would be the same value as here because the slope is same. QA dP P naught by W times e power VEB over VT. This is another important equation. Now, coming to the last, that is ICN. ICN is the current that is flowing because of the minority carriers electrons in the collector crossing this depletion region, which is nothing but the reverse saturation current just because of the electrons going from collector to base side. That can be written as ICN is equal to QADC NC naught over LC. This is another important equation. Now we know even IC because we found the expressions for ICP and ICN. Now let me scroll down. In fact, if you observe here, IEP is equal to ICP here. The reason being, we assume that W is very small compared to the diffusion length of holes in the base. So when we assume the depletion width is very small, the recombination current can be neglected, in which case IEP would be equal to ICP. That's a valid assumption in this condition. Now, we had a term that we defined as emitter injection efficiency, which was given by gamma star, which was in fact equal to IEP over IEP plus IEN. In fact, we can say this is IEP over IE, which is equal to, as we know the components now, we can find what is gamma star in terms of device parameters. We can rewrite this equal to 1 over 1 plus IEN over IEP, which is equal to 1 over 1 plus IEN, let's substitute this value here, divided by the IEP, which is QADP P naught over W times e power VEB over VT. Now we know that the emitter junction is in forward bias, in which case this term would be approximately equal to this term, because this one would be very small compared to this exponential value as it is in forward bias. So in that case, we can cancel these two terms, and QA are common. Let's cancel them. Now we can rewrite this expression as gamma star is equal to 1 over 1 plus DE naught times W over dP times Pn naught times LE. This is another important expression. Now, if we observe here, now gamma star can be written in terms of doping concentrations instead of the minority carrier concentrations here. From this, we can figure out that gamma star can be close to 1 if NB over NE is as small as possible. That's one of the reasons why the doping concentration Ne is made very, very high compared to base doping concentration. Now, in order to improve the injection efficiency, we have to make sure W is as small as possible. That's the reason behind the base width, making it as small as possible. In fact, we have found all the current equations here in terms of device parameters and the voltages applied across the junctions. Now, for a very important reason, we are going to take all these equations and represent in a particular format so that it will be used to understand Eber's mole model in a very effective way. So in order to do that, let me write all the equations in a systematic way. We know IE is equal to IEN plus IEP. We have just found the equations for both of them. So let me put those values here. So this is equal to this term, and this is equal to this term. But we're going to add few more terms, that is, subtract AQDP naught over W plus AQDP naught over W. So the equation remains the same, but only thing is we want to get this form here as well. So this can be reduced to AQDENE naught over LE plus AQDPPN naught over the depletion width times e power VEB over VT minus 1 plus AQDPPN naught over W. So this can be written as IE is equal to, so we can say this is the emitter junction leakage current, that is IE naught times e power VEB over VT minus 1 plus AQDP naught over W. In fact, this equation will be used when we go and discuss Eber's mole model in the next video. Coming to the second equation, which is IC is equal to IEP plus IEN, which is equal to AQDP naught over W times e power VEB over VT plus AQDC and C naught over LC. Of course, here this term is equal to this term that we have derived, and this term is equal to this term. Now we are going to subtract and add a term, which is this term. So we can rewrite this expression as IC is equal to this term minus this term. I can take this term common, where I would get AQ dP Pn naught over W times e power VEB over VT minus 1. Now we are left with these two terms. Let me add that up, which is this term we can say as the IC naught, which is basically the leakage current if there is only the collector base junction present, and that leakage current would be this IC naught. So the collector junction leakage current. We can further reduce this equation into IC is equal to AQ dP Pn naught over W times e power VEB over VT minus 1 plus IC naught.